Good afternoon, everyone. So today's talk is about VirtualSAN performance troubleshooting. We all know that VMware VirtualSAN provides a single storage pool for all hosts in the cluster by aggregating the SSD flash drive and hard disk drives in the cluster. And IOs from the VM is distributed and balanced across the hosts in the cluster that's connected by high-speed inter-host connection. VirtualSAN provides solid performance for various workloads in the most of time. However, from time to time, it may experience unexpected performance issues due to the complexity nature of VirtualSAN. Today, Regine and myself, Zach, are going to give you a guidance of how to do performance troubleshooting for vSAN. Both of us are from the VMware performance engineering team. We interact with VirtualSAN developers on a daily basis. We also handle customer performance issues that need engineering efforts. Let's look at today's agenda. First, we are going to start by having an overview of VirtualSAN architecture. Then I will hand over to Regine for him to talk about the first troubleshooting tool, VirtualSAN Observer, and the first example for troubleshooting performance issues. Next, I will come back and talk about the newly released performance service tool that is integrated with vSphere Web Client. I'm also going to show you two more examples for troubleshooting performance issues for read and write workload, respectively. Finally, we are going to conclude by summarizing the troubleshooting workflow we use in today's example. So here is a diagram of VirtualSAN architecture. The VM issues an I/O, and that I/O is handed over to virtual SCSI layer in ESX host. Then that I/O enters VirtualSAN from DOM client layer. DOM stands for Distributed Object Manager, and it is responsible for coordinating inter-host traffic in vSAN. Then the client passes that I/O to DOM owner, which is usually on the same host. Owner sends the I/O through network to component manager, that is usually on a remote host. Then component manager sends down the I/O on the local host to LSOM layer in VirtualSAN. LSOM stands for Local Log Structured Object Manager. And LSOM is responsible for aggregating the SSD drives and the hard disk drive on a particular host to form a disk group. LSOM also implements the I/O interface to those disks. Before we take a further look at LSOM, it is worth to mention the newly released features in VirtualSAN 6.2. First, for better data integrity, 6.2 introduces a software-based checksum, and this is implemented in DOM client layer. Then, for all-flash setup, 6.2 also introduced erasure coding feature for better space efficiency. And this is implemented in DOM owner layer. Finally, to achieve even better space efficiency, the all-flash cluster also have the deduplication and compression features available. And that is implemented in the LSOM layer. Now let's look at a simplified diagram of LSOM layer. LSOM layer has two sub-tiers, the caching tier of SSD and the capacity tier of hard disk drives. When a read I/O reaches LSOM, VirtualSAN first look up the data in the caching tier, which is partitioned to be read cache and write buffer. If the data is there, the I/O is served directly from there. However, if the data is not found, VirtualSAN has to fetch the data from the slower capacity tier and then write that entry into read cache. If read cache is full at that point, the least used entry is evicted. On the other hand, when a write I/O reaches LSOM layer, the data is staged directly to write buffer and returned to the upper layer. And the data is later destaged or drained from the write buffer to the capacity tier asynchronously. It is worth mentioning that the dedupe and the compression feature is implemented in this destage process in the all-flash setup. Also, for the all-flash setup, the whole of the caching tier is used as a write buffer. There is no concept of read cache in all-flash setup. And the read I/O are directly fetched from the capacity tier SSDs. OK, now we have an overview of the VirtualSAN architecture. Let's welcome Regin for him to talk about the VirtualSAN Observer.
Thanks, Zach, for the introduction and the overview. Now, I'm going to talk about the first performance troubleshooting tool of today's talk, VirtualSAN Observer. Many of you guys might have already used it before, but some of you might not. So let me first give a brief introduction of the VirtualSAN Observer. Like I showed on the slides right now, it's a screenshot from the VirtualSAN Observer. It basically is a web page, consists of a lot of performance data. Later, we are going to zoom into each part and see what's inside it. But for the introduction, the VirtualSAN Observer is designed to capture comprehensive performance statistics for VMware VirtualSAN cluster. It also provides the web UI, like I show here, for you guys to view the live data. So with the VirtualSAN Observer, customers like you guys can easily understand how VirtualSAN behaves in your own environment. It actually enables you to identify the potential issues within your setup. And then you can either reconfigure or replace your hardware if it turns out to be a hardware issue. Or you can pack and send those VirtualSAN Observer data back to VMware tech support for further help. So the number one benefit of the VirtualSAN Observer is that it can easily generate offline bundle. With the offline bundle, you can view the performance data even after the experiment. So you can use the offline bundle as discussion materials with your colleagues or with the VMware tech support team. And the second benefit for the VirtualSAN Observer is that it's actually available from the very first release of VirtualSAN. That means if you want to compare the performance, if you want to see what performance changed when you upgrade from previous version to the latest version, the VirtualSAN Observer is the place to go. Lastly, the VirtualSAN Observer relies on the Ruby vSphere console to run. So Ruby vSphere console, also known as RVC, comes bundled with both Linux-based vCenter server appliance and Windows-based vCenter server. Those are two commands to launch the RVC. All you need to know is the username and the IP address to the vSAN cluster that you want to monitor. Once you are inside the console, the command to initiate vSAN Observer is uniform across platforms. It's called vSAN.observer. observer plus the cluster name for the VSAN cluster you want to monitor. There are several helpful options for this command for you to use. Here I highlight some of them. For example, -R will tell the command to run the web server so that you can view the live data via browser. -K will tell the command to just keep the performance data inside the memory and then delete those data after the command exits. So if you want to save the data for later usage, you can give -F plus the output file name, then all the observer data will be saved to that file. One major concern of doing that is the space consumption. So that's why this command also provides several other options for you to manage the space. For example, you can specify the maximum disk space for that output file. Once that file reaches the threshold, you will simply remove the first entry from the file and add the new entries in. Besides that, you can also specify the interval for the virtual SAN observer. So basically, by default, virtual SAN observer will collect the performance data in every 60 seconds. So you can reduce that number to get more fine-grained performance statistics. But of course, the output file size will be very large. You can also increase that number to save the disk space. Lastly, it also gives you the option to generate the HTML-based full offline bundle for you to use. So once the virtual SAN observer is run, all you need to do is to open the modern browser and input the web URL I show on the slides here. It consists of the vCenter server hostname or the IP address plus the port number. By default, the port number is 8010. You can, of course, reconfigure that using the options for the virtual SAN observer command. So now we know how to run the virtual SAN observer. How is that mapped to the virtual SAN architecture? Right now on the slides, the right-hand side is the architectural diagram for the virtual SAN that Zach has described in previous slide. And the left-hand side is the tabs from virtual SAN observer web page. So here, the DOM client layer actually mapped to the vSAN client tab, and similarly, DOM owner layer mapped to DOM owner tab. And the DOM component manager layer maps to the vSAN disks tab, and the LSON layer maps to vSAN disks deep dive. Notice that there are several tabs in the vSAN observer that is not in the architectural diagram. Those are actually the shared resources among virtual SAN components. For example, there's a pCPU tab, which will show the CPU usage for all the processes inside the virtual SAN cluster. Similarly, the memory tab will show you the memory consumption for all the processes inside the virtual SAN cluster. And also, there's a network tab, which will show you the network-related statistics, like the transmission rate and receive rate, and also it will give you the TCP errors. Also, there are some other tabs, like the VMs tab. It actually shows you the viscosity stats from the VM's point of view. And also, there's an advanced tab called VSAN More. Inside it, you can find out various types of congestion inside the cluster. Also, you can find out the component distribution within the virtual SAN cluster. Now let's look into each one of them. For DOM client layer, DOM owner layer, and the DOM component manager layer, virtual SAN observer will show you 6 key performance statistics for each host. Those performance data are the latency, IOPs, bandwidth, congestion, outstanding I/O, and the latency standard deviation. Note that the virtual SAN observer actually reports the average data within the sampling period. So for example, the latency value here shows you the average latency within the sampling interval that you specify. However, the latency standard deviation here shows you how the latency value fluctuating within the sampling period. We're actually going to use that value later in our example. Now for the LSON layer, things get more complicated because it actually implements a two-tier storage architecture. So let's look inside the VSAN disk deep dive. The first thing you will see is a host level disaggregated stats, including the basic stats like latency, IOPs, and bandwidth. It will also show you storage-related stats like read cache hit rate and the number of evictions. And then you can also find out the performance statistics from the caching tier. It will tell you, again, the latency and IOPs, but it will also tell you the usage for the write buffer. We also call it write buffer fill percentage. Also, if you want to know more, you go inside the full graphs. It will tell you more detailed data like the jamming rate from the caching tier to the capacity tier. Lastly, it will also tell you the capacity tier statistics. Know that if you want to know more, you go inside the full graphs. It will tell you data like the read performance, the write performance. So now that we know how to map the VSAN architecture to the VSAN observer, let me use an example to illustrate how we can use this tool to do performance troubleshooting in real world. The example we use here is the performance degradation caused by network errors. In this example, we set up an all-flash cluster with 4 hosts. Those hosts are connected to 10 gigabit Ethernet network. And by default, Virtual SAN has the host fault tolerance feature enabled, HFT equals to 1. That basically means for each data block in the cluster, there will be a replica. So the write I/O coming from the VM will have to go to 2 places in the cluster. So inevitably, one of the I/O will travel through the network. Right? So the workload we use here is a sequential write, 64 kilobytes I/O size. It can somehow mimic the VM clone operation. So the problem in this example is that after 30 minutes, one of the hosts start to experience high latency and low IOPs. So you can imagine, for the VMs that has component on that host will also experience the same high latency and low IOPs issue. Now this is the situation we are facing. How can we do the troubleshooting? To do the performance troubleshooting, we always go back to the VSAN architecture diagram, and we start at the very top layer and identify the performance issue. And then we work down the layers inside the architecture diagram and identify the last layer with a performance issue. And then we focus on that particular layer and find out the root cause. So in this example, we know that one of the hosts are experiencing high latency issue. So we start from the DOM client layer. In the observer, we call it VSAN client tab. And here we find out that for one host, it actually experienced very high latency after around 30 minutes into the run. Consequently, the IOPs and bandwidth dropped to almost 0. So this actually verifies the findings we have. One of the hosts experienced high latency. And one thing worth noticing is the latency standard deviation value here. It's also high during the problematic period. That actually tells us that not all IOs from that host are experiencing high latency. Right? Only a portion of it experiencing very high latency, and the rest of the IO are actually fine. Then we go on and look at all other hosts in the cluster. We find out that only one host experiences high latency. The other hosts are actually fine. So what we learned from this layer is that, okay, one of hosts are experiencing high latency issue. And what will cause it? Now then we work down the architecture diagram and look at the next layer, which is the DOM owner layer. We find out that the exact same issue manifests in this layer too. This tells us that the issue is not coming from the VSAN client layer. The issue are coming below it. So that in the performance troubleshooting process, we can rule out the first layer. So the root cause won't be there in the VSAN client layer. Then we further work down the diagram and reach the VSAN disks, which is also known as DOM component manager layer. In this layer, we find that the latency is actually fine in this layer. So the problem is not coming from VSAN disks layer. Notice that the IOPs and bandwidth actually drops. This is simply because the higher layer stop issuing IO to this layer. It does not mean there's a problem. So from here, what we learned is the performance issue is not coming below the VSAN DSys layer. Right? So we can rule out them for the fuller root cause. Now we should focus on the layers between the owner layer and the VSAN DSys layer. What's between them? There are two possibilities. One, it could be because of the CPU. Right? It could be because the CPU that is used to run the DOM owner processes got saturated. So the DOM owner process does not get enough CPU time to process the I/O. This will actually lead to high I/O latency. So is that the issue for this case? To verify that, we need to go inside the pCPU tab. And then in this example, we find that all the process has very low CPU usage. So this is not the root cause for this example. So the second possibility is the network issue. Remember, at the beginning, I mentioned we have HFT1 enabled. So at least one of the I/Os, write I/O from the VM needs to travel through the network. So we have to verify that. To do that, we go inside the network tab. And here, we find out that for the problematic host, the PNIC transmit rate actually dropped to very low level when there's a problem, high latency problem. Also, we are seeing very high TCP errors. Notice that there are two colors here. The blue color in the TCP errors means that that host has problems sending out the data. And the orange color means that that host has problem receiving the data. So what we learned from this graph is that one of the hosts has problems sending out the data, and the other host cannot get proper data. To understand more, we need to go inside the full graphs. So here we find that during the problematic period, that particular host has very high dual-back RX stats, which will further cause retransmits. So let me explain this further. So dual-back RX means that this host receives duplicated acknowledgement from the receive end. The receive end will do that only when they cannot get the correct packets. So this will trigger this host to retransmit those failing packets. And all the I/Os with those retransmitted packets will experience high latency. So until this point, we figure out the problem, the root cause in this particular example is the PNIC problem. So when we replace the hardware, we actually resolve the issue. Now let's take a recap and see what we have done in this example. We worked down the virtual SAN architecture diagram and find out that there's latency increase and IOPs and throughput drops in the top layer, the DOM client layer. And then we find that the issue also presents at the DOM owner layer. However, the issue is gone in the DOM component manager layer. Then at this point, we need to focus on the layers between DOM owner and DOM component manager. There could be two issues. It could be because of CPU, or it could be because of networking. In this example, the root cause is actually from the network. So here, I classified and summarized the possible network issues into three categories. The first one is the resource contention. It is simply because the VSAN share the network with other workloads in the data center. And those other workloads keep sending out a lot of packets and cause the link congestion. Also, it can be because the CPU and memory contention within the VSAN cluster. And the second category is actually the hardware issue. So this network issue can simply be caused by the faulty network switch or simply the unstable network link. The last category is the misconfiguration. So all the misconfiguration either inside the network switch or in the host site will all cause the packet drop and will lead to very high I/O latency. So with that, we have finished the first example in this talk. Remember that I've used a virtual SAN observer to solve this issue. There are so many benefits to it. However, there's an inconvenience with the virtual SAN observer. So the virtual SAN observer actually uses file as a media to save the performance data. So for customers who wants to write their own scripts to continuously monitor a particular metrics within the virtual SAN cluster, it's very hard to do. It's doable, but it needs a lot of hacks. So that's why we have a newly released performance troubleshooting tools, which is called the VSAN Performance Service. Now, I will hand over to Zach. He's going to talk about the new released tool.
Thank you, Regine. Let's start from looking at the screenshot of performance service in vSphere Web Client. So performance service provides common metrics collection at available layers. Those common metrics include IOPs, latency, throughput, and outstanding I/O. For each of these metrics, the collection is sampled at 5-minute granularity. And the value is calculated in a similar way as Virtual SAN Observer calculates it. For each of these metrics, Virtual SAN Performance Service provides a single plot for it. And this plot can cover a duration up to 24 hours. A user can actually select the start time and the ending time of a single plot. Performance service holds up data for a long duration. It actually holds up these performance data for 90 days before it rolls over. It is also very easy to enable performance service from vSphere Web Client. To do that, a system administrator or a user just click on the cluster that he or she wants to have the performance service, and then go to the Manage settings of that cluster, and then navigate to the Virtual SAN related settings. Over there, just edit the health and the performance settings. In the popped-up dialog box, just check the box of Turn on Virtual SAN Performance Service, and then apply appropriate storage policy. By clicking OK, what's happening behind the scene is that a database is created on Virtual SAN data store itself, and the metric collection is started immediately. Since the metric data is put into a database, there is actually API available in 6.2 release to query this performance data. This is one advantage over Virtual SAN Observer. Performance service also provides very flexible viewing at cluster, host, and the virtual machine view. I find the host view to be most useful in performance troubleshooting process. It's also very easy to access host view. When just click on any host in that cluster, and then go to Monitor Performance tab. Over there, there are 4 layers available for performance metric data. All the common metrics are collected for these 4 layers. And some advanced metrics are collected for Virtual SAN disk group layer. Each of these layers also maps to 1 or 2 layers in Virtual SAN architecture. For example, virtual machine consumption maps to vSCSI and DOM client layer. Virtual SAN backend maps to DOM component manager layer. Disk group maps to LSOM layer, in particular, the caching tier statistics. It contains advanced metrics such as read cache utilization, write buffer utilization, destaging throughput, and so on. Finally, the Virtual SAN disk maps to the physical disk usage for the caching tier and the capacity tier disks. Now we have an overview of what's available in performance service. Let's see it in action. In example 2, we have the most common workload, which is the random read workload. And this is done by on a 8-node VirtualSAN hybrid cluster running 6.2 release. The workload is running on the first active VM on each host, and the default VirtualSAN storage policy is used. The workload actually starts fine in the first hour. Then it suddenly experiences IOPs drop and the latency increase. Now let's do the performance troubleshooting. Remember, we always start from the top layer available in VirtualSAN architecture. In this case, we start from the virtual machine. We look at the virtual SCSI layer statistics. We find the IOPs drop is present. Also, the latency increase is present there as well. Then we walk down to the next available layer in VirtualSAN, which is a DOM client layer. We find that the IOPs drop and the latency increase is present as well. And then we check the next available layer, which is the component manager layer. The issue is present as well. Then we further go down to the next layer, which is LSOM layer. We check the IOPs there. We find that the drop is present there. Since this is a read workload, we check the read cache utilization. In particular, we find that the read cache hit rate drops by 20% when the IOPs drop happens. This means a good portion of the reads is fetched from the slower capacity tier. And that is why the IOPs drops to a lower level and the latency increases dramatically. We take a further look, and then we find that there is also a large amount of read cache evictions while the problem is happening. This indicates the read cache is full. And then at this point, we come back to the virtual machine consumptions and check the other VMs on the same host. We find that there is a second VM on that particular host that has read activities going on when the problem happens. And this makes the read cache to be full and causing the read cache entry evictions. Now we have root cause the issue of this performance issue, which is from workload change from the second VM. Let's fix this read cache eviction. This can be done by applying read cache reservation policy to the first workload VM. We just create a new customized VirtualSAN storage policy by setting the flash read cache reservation to be 100%. And then we apply that policy to the first workload VM and wait until the policy change finishes. Please note that once we apply this policy, the particular amount of read cache is now dedicated to the VM and cannot be shared by other VMs in the cluster. After doing this, we come back to check the workload performance from the virtual machine view. With the second VM read start at a similar time, we observed that the high IOPs of the virtual machine is sustained, even if the second VM read is present. By the way, this second VM read turns out to be some backup program that is reading from VirtualSAN storage. More importantly, we find that the read latency is capped below 3 milliseconds. So at this point, we have root cause the issue, and we find a resolution for this particular issue. Let's take a quick recap of the performance troubleshooting steps we take in this example. We first start from the virtual machine level, which is the top layer in virtual SAN architecture. Then we walk down the layers in the architecture. We find the issue is present in DOM client layer and also in the component manager layer. Then we check the LSOM layer. Since this is a read workload, we check the read cache utilization. We find there is read cache hit rate drop and read cache evictions. Then we go back to the virtual machines and find that there is workload change that's from second VM. Finally, we apply the customized storage policy with read cache reservation to make sure that the workload from first VM is sustained. Okay, this concludes this read cache example. Next, let's look at another common workload, which is a random write workload. Again, this is running on an 8-node hybrid cluster that has a Virtual SAN 6.2 release. Then there are 6 hard disk drives in each of the disk group. And the workload is large block random writes. Again, this is using the default Virtual SAN storage policy. The problem present is that throughout the testing duration, we are seeing high latency and low throughput for the workload. So we just follow the troubleshooting steps we mentioned. And then we start from the virtual machine level, and we identify the issue or the symptom, which is high latency and low throughput. Then we walk down the layers. We find that DOM client has the issue present. DOM component manager also have the issue present. Then we enter LSOM layer. Since this is a write workload, we check the write buffer utilization. And we find that the write buffer has only 20% free space. At the same time, this staging is constantly going on, but the throughput is very low. There is nothing wrong about this. This is just saying Virtual SAN is busy at the write buffer layer, and the performance issue of low throughput is present over there. And then we further walk down the architecture and hit a bottom physical disk layer. We check the first physical disk in the capacity tier. We find that it is actually doing fine and serving a good amount of write IOs. And then we check the second hard disk drive there. However, this hard disk drive is only having 0 write IO. It's idling there. And then we further check the third one and all the rest of hard disk drive in the same disk group. They are all idling. So there is inactive hard disks, and this disk group is underutilized. By this point, all of you may have already realized that the low throughput performance is actually bound by the single hard disk write performance. And the reason behind that is because we are using default Virtual SAN storage policy for the VM, which has a stripe width set to be 1. And in this particular example, the data component of that VM disk is spread across only 1 hard disk drive. And this problem can certainly be mitigated by setting higher stripe width values. Similarly, we create another customized storage policy and setting the stripe width equals to 4. And then we apply this new policy to the workload virtual machine. And then we wait until the policy change finishes. Then we check the virtual machine performance again. We find that the throughput is actually tripled, and the write latency is actually less than half of what it was. And of course, when we check the capacity tier physical disk usage, we find more active hard disk drives over there. By the way, all the storage policy change can be done online without interrupting the production workload. So this concludes our final example here. Now, let's conclude our talk by summarizing the troubleshooting workflow we have. Like what we do in all the three examples, we always remember the virtual SAN architecture and start from the top layer over there. It can be virtual machine or DOM client. And then we identify the issues there. The issue can be low throughput, low IOPs, high latency, or any combination of them. Then we simply walk down layer by layer in virtual SAN architecture. We try to find the lowest layer, or the last layer has the performance issue present first. It can be between two DOM layers, or it can be all the way down to the LSOM caching tier or the physical disk layer. After we identify the layer that has the problem first shows up, we just focus on that layer and check for related entries in that layer that could lead to the performance issues. For example, if it's between two DOM layers, check for the CPU, related CPU thread utilization. See if it is CPU bottlenecked. Also check for network traffic and network errors if there is inter-host traffic involved. And also check for competing traffic, such as resync traffic that's running at the background, or if there is other VM rather than the workload VM that introduce competing traffic. If the problem is down to LSOM layer or the physical disk layer, check for evictions or read cache hit rate if it is read workload. And check for write buffer utilization and the destaging throughput if it is the write workload. And also, if it's down to physical disks, check the physical disks IOPs and the latency, see if they are doing fine. And also, if it is possible, check for component distributions, see if there is any imbalanced distribution that could lead to the performance issue present. And orthogonal to all the above, always check for host level memory consumptions and the CPU utilizations, because the performance could be bound at host level by memory or CPU. Okay, this is today's takeaway point. I wish you can take this workflow together with a virtual SAN architecture diagram and get a better performance for your virtual SAN cluster. If you want to know more about virtual SAN, right now here at VMworld, there are a number of exciting sessions going on. For example, there are sessions about the last 6.2 release new features and about the future of virtual SAN. Or you can know more about networking design and the sizing, or simply get more troubleshooting tips. Also, it's worth mentioning that we have a newly available VMware storage technology portal available, which is storagehub.vmware.com. You can go there and check out the blogs and the white papers for VMware VirtualSAN. Finally, we have the documentation to Performance Service API and the KB article for using VirtualSAN Observer available. OK. Now we can take questions. If any of you have questions, please take the microphone at the middle.
Yes, I have a question.
Yeah.
So you said the stripe size, I mean, was today 1 to 4, right?
Yes.
So what is the stripe block size? Means that how big the I/O goes into this disk and goes next? Like what's the size of the I/O?
The I/O size in this workload is 256 kilobytes.
Okay, so on each I/O you go to next disk, like a round robin for each I/O?
I believe internally it should be some round robin algorithm, but I'm not 100% sure on top of my head. Right?
Okay.
Yeah.
And also, you said that you can, in the middle of the I/O, you can change those settings, but how do you balance that after if, because this will be unevenly used. Are you going to,
right.
Yes. Are you going to rebalance those?
Sorry, under the scenario that disk is unevenly used, what is the particular question there?
Yes, this size will be unevenly used capacity. So in the back end, do you have like a rebalancing process going on afterwards, or?
If the disk is actually, let's say the disk is unbalanced used. Right?
Yes.
VirtualSAN CLOM layer actually provides this rebalance from time to time. So there is a daemon at CLOM layer, and it will check the disk usage across all the hosts in the cluster. And if it finds the imbalance is too bad, it will kick out a rebalance process, right, which is running at the background.
Right.
Okay.
All right. Thank you.
Sure. Sure.
With the inactive disks, is that pretty much just limited to hybrid arrays, or is that possible in all flash arrays also?
Sorry, I didn't get the first part, first part of the question.
So in your final troubleshooting scenario with the inactive disks, with the low throughput, because one capacity disk is taking all the writes.
Right.
Is that pretty much only a concern in hybrid arrays, or can that happen in flash arrays also?
That applies to all flash setup as well, because for all flash setup, there is also concept of write buffer. In fact, as I mentioned, the whole of caching tier is used as write buffer, right? So actually, it is a very good idea to check for the write buffer and the destaging throughput for all flash cluster.
So is it your recommendation to increase stripe width as a default, or start at 1 and watch for performance issues?
The default policy actually will work for most cases if you have multiple VMs and multiple disks in the cluster. It is a bottleneck for this particular example because for each of the hosts, we only have one VM with one disk available there. Right. For this particular example, we are just showing how do you find where the issue is. Right. And the default policy actually works well for most of the case, unless this is some extreme configuration like what we have in this example.
Okay, then one last question.
Sure.
So then stripe width would be limited by the number of capacity disks that you have. So if you only have 4 capacity disks, you can never set stripe width higher than 4.
That is sort of correct, I think.
Yeah. So our choice is best to apply the stripe width, but not guarantee.
Okay, thank you.
You mentioned I need to turn off the performance manager. It creates a database in the background. How much data is stored there? Because you said it stores 90 days. What happens if I have 2,000 VMs? What is that going to be the implications for my disk?
Yes. That's a very good question, actually. So to give you an example or a feeling of how large the data is, we have this 8-node cluster, and we constantly have workload running on a daily basis, like those FIO or IOmeter micro benchmark. And then over a 3-month time duration, I checked the disk usage of the database, of the performance service database. It's only 400 megabytes, actually. So I would say it's actually safe to use that. And the whole purpose of putting the performance service database on VirtualSAN data store is meant to say, keep the data for long enough. Okay. Well, thank you all for coming. So if you are encouraged to fill out the survey, available at the end of the VMworld.